Math isn't difficult. Math is fun. I am Neelakanta Bhanu Prakash and I am the fastest human calculator in the world. And we are exploring infinities. Exploring infinities is here in front of you to give you a mathematics learning experience like never before. With expert trainers from around the country, we are here to make you learn math the right way.
Hello, I'm Anshika from Exploring Infinities, and I'm here to help you with the basic concepts of mathematics and make it look like more fun and interesting in some way or the other. Okay, so we'll start off with the chapter linear equations in two variables. So, what exactly is linear equation in two variables? So, as you can see, two variables means two things. Somewhat you're going to play with two variables in the entire chapter. But before that, let's see what exactly is one variable. So you have 100 rupees, you just go to the market, you give 100 rupees to shopkeeper and ask him to get you Kit Kats. Okay, so he informs you ki, the Kit Kat the cost of one Kit Kat is 25. So now the dilemma in front of the shopkeeper is how many Kit Kats should he give you. So he just assumes, okay, so he has given me, the child has given me 100 rupees, so 100 rupees I should get him, like, let the number of my Kit Kats that I should give to this child be X. So he just assumes the number of Kit Kats to be X. Okay, so let's start writing these things down. Number of Kit Kats. Okay, so now what shopkeeper thinks is, if my each Kit Kat cost 25 rupees, if I multiply this X by this 25, I'll get 100. So if he solves this, he'll get X to be 4. So he decides that, okay, I should get this child 4 Kit Kats. So that's the number of Kit Kats that the child gets for worth rupees 100. So now this was linear equation in one variable, where you actually play with just one variable, probably x, y or anything, and you can like directly solve it and get the answer. So now what you do is, you have 100 rupees, you go to the market, instead of buying just Kit Kats, you decide that you'll get mangoes and strawberries. So mangoes and strawberries, the shopkeeper tells you the cost of one mango would be 5 and the cost of one strawberry would be 10. So now the shopkeeper's problem is, how many mangoes and how many strawberries should I give this child? So now what he does is, he assumes the number of mangoes to be X and number of strawberries that he should give to the child to be Y. Okay, so now what the shopkeeper does is, if one mango costs 5 rupees and if the number of mangoes I should give to this child is X, so 5 into X gives you one part, plus if one strawberry costs 10 rupees, multiplied by the number of strawberries this child will get, Y, equal to 100. So his problem is, he has to solve this equation to get the number of mangoes and the number of strawberries that he should give to the child. So this is linear equation in two variables. So in this entire chapter, we'll be studying about these kind of equations where we have two variables, and our problem will be to solve such kind of equations. So let's just hop into the main topic. Okay. So, for example, your name is Tom. Okay, your name is Tom. You have a sister named Dana. So, what you do is, you want to play cricket. So, you go to the market, get bat and balls. So, you get 3 bats and 2 balls, and it costs you 80 rupees. Okay. So, your name is Tom. You have 3 bats, 2 balls. It costs you 80 rupees. So, your bats and balls were very fancy. So, your sister Dana also wants to buy those bats and those balls. So, she goes to the same shop, asks the shopkeeper to get you those very same bats and balls. Then she gets 4 bats and probably 3 balls, and it costs 110 rupees. Okay, so let's start writing it down. So Tom went to the market, Dana went to the market. He gets, okay, bat and ball. Tom gets 3 bats and 2 balls. Dana gets 4 bats and 3 balls. Okay, so this entire thing costed Tom 80 rupees and Dana costed 110 rupees. So now when they both get back home, their mom asks them ki what exactly was the cost of bat and ball. So it means she's asking you the cost of one bat and one ball. It means let's assume the cost of one bat be X and one ball be Y. So this was the entire problem ki the number of bat he has multiply the cost of one bat plus the number of balls he has multiplied by the cost of the ball equal to 80. Similarly, for Dana, it will be 4x plus 3y is equal to 110. So now their problem is they have to get the values for x and y. So Tom, being the first one to go and get these bats and balls, he says, mother, probably my bat costed 10 rupees. Okay. So he's saying that x is 10. So let's see what will be the value for y. That is, what will be the value for the ball. So let's solve this equation. 3 into 10 plus 2y is equal to 80. Okay, so now he has 2y is equal to 80 minus 30, that's 50. Therefore, y they have is 25. So now the value for their bat is 10 rupees and ball is 25. So this was Tom's guess. Okay. Tom guessed somewhat like this, that x is 10 and y is 25 according to his calculations. So since Dana also bought the same bat and ball, her equation should also satisfy the x and y's, because it was the same bat, same ball, same MRP, same cost, everything's the same. So this x is equal to 10 and y is equal to 25 should satisfy Dana's equation. Okay, so let's see Dana's. If you want to satisfy an equation, it means LHS should be equal to RHS. So if I put the values for x and y, I should get my LHS should be equal to 110. So let's see if I'm getting it or not. So I put it into the Dana's equation. So I have LHS as 4 into 10 plus 3 into 25. So I have 40 plus 75, which gives me 115 and not 110, which was the RHS. So it means that my 10 and 25 is not satisfying Dana's equation. It means Tom's guess was absolutely wrong, because they both bought the same bat and ball. So x and y should give you the same value for both the equations. Okay, so this means that if you have one linear equation, like just a single linear equation with two variables, that is 3x plus 2y is equal to 18, you can get many solutions. Like in this case you are getting 10, 25. But if you need a proper answer to your situation, like in this case you need the cost of bat and ball, you need two equations simultaneously together with two variables, so that you can get a unique solution, that is a unique answer to your cost of bat and your cost of ball. So let's see. So we'll develop a method by ourselves using probably circles, squares, rectangles, and see what exactly is the value for x and y, and what exactly is the cost of a bat and a cost of ball. So we'll call this method model method. Okay. So in my model method, what exactly we do is we represent our equation in the form of shapes, koi bhi, any random shapes. So if I start representing Tom's equation in random shape, I have 3 bat and 2 balls for him. So let my bat be somewhat like squares and the balls be circles. So if I represent it, it will be somewhat like this. So 3 boxes and balls be 2 circles. Okay, and if I represent Dana's equation, it will be like this with 3 balls. So this is costing 80 rupees and this is costing 110. So now what we do is we want to equate two things together. We want to eliminate one of them. So what we do is we choose one of them, either bat or ball. So I'm choosing probably ball. Okay, so I'll now make this 2 equal to something which is also equal to this 3. Yani, what I'll do is I'll multiply this by something, I'll multiply this also by something, such that I get the same answer over here. Okay, so what we do in such cases is, this is 2 and this is 3. So nearest multiple what we have is 6 for 2 and 3. So we try making it 6. So what do we do exactly to get 6 when you multiply it by 2? So you'll get 2 into 3 equal to 6, and you'll get 3 into 2 to be equal to 6. So if you're multiplying your one part of the equation by 3, then you'll have to multiply the entire equation by 3 so that it remains an equation. Okay, so what I do is, my first equation, that's Tom's equation, is now multiplied by 3. So if it's multiplied by 3, this 3 boxes will also get multiplied, 80 will also get multiplied. So what I'll get is, my 3 boxes are get multiplied by 3, I'll get 9. If my 2 circles are getting multiplied by 3, I'll get 6. So I have these 6 with me, 6 balls. Similarly, I have 80 into 3, which is equal to 240. So this is my Tom's equation in the model method. Similarly, if I try developing Dana's, I have multiplied my balls by 2. So I'll multiply the entire equation by 2. So what am I getting? It's 4 multiplied by 2, that's 8. I have 3 balls multiplied by 2, that's 6. Now I'll get 110 multiplied by 2, that's 220. So what I do now is, I have same number of balls for both Tom and Dana. So I just eliminate them, that okay fine, they have nothing to do. So now you can see is, Tom has one extra bat with him. Okay, one extra bat. And you can see from here that cost of that one extra bat is 20. Why? Because Tom is paying 20 rupees more than what Dana is paying. If you can see in this equation, they have both bought the same number of balls, but there's one extra bat with Tom. So what you do is, that extra amount that Tom is paying is the cost of that one bat that he has bought more than Dana. So it means that one extra bat is costing him 20 rupees. Okay, so now we have the answer for our x, that our x is 20. And now using our x, if you put this x into any of the equation, be it 3x plus 2y is equal to 80, or be it 4x plus 3y is equal to 110, you'll get the same answer for y. So let's see, I'm putting it in the Tom's equation. Okay, so if I put it into the Tom's equation, initial equation, it's 3 into 20 plus 2y is equal to 80, which will get me 2y is equal to 80 minus 60, which gives me 2y is equal to 20. This gives me y is equal to 10. So now I have the answer, x is equal to 20, y is equal to 10. So let's just check if in this time, do we have the right x and y. Our cost of bat and ball should be same for both Tom and Dana. So we have this one extra bat with Tom, which costed him 20 rupees. So we have x with us, y with us, using Tom's equation. So let's check if Dana's equation is also satisfying this or not. So in Dana's equation, I have LHS as 4x, that's 20 now, plus 3y, that's 10 now. So I have 80 plus 30, which is equal to 110. And which was equal to our RHS, as we know. So it means that this time, in this model method that we have developed, we have the right answer. We have a solution to our pair of linear equations. That is, our solution is 20 and 10. Why? Because this particular answer is satisfying my both the equation of Tom and Dana. Therefore 20 and 10 is a solution of our pair of linear equations. That is, this two linear equations we had, now we have a solution to those pair of linear equations. So if we try generalizing what exactly is linear equation in two variables, so we can say that the general form will be somewhat like ax plus by plus c equal to 0, where your both a and b are not equal to 0, that is, it should be like a square plus b square is not equal to 0, and a, b, and c should all be real numbers. Okay, so what exactly happens when your a or b becomes equal to 0? If your a becomes 0, your entire ax terms become 0, so you have by plus c equal to 0, and by plus c equal to 0, as you know, it's linear equation in one variable. So the entire concept of linear equation in two variables just vanishes if your a or b becomes equal to 0. Similarly, if b becomes equal to 0, we again have a linear equation in one variable. So therefore, in general, ax plus by plus c should be equal to 0, where a and b should not be equal to 0. So what you can say is here a, b, and c are constants, okay, and x and y are variables. So it's not necessary that every time you have x and y as your variable. It can be m, n, p, q, anything can be variable, and a, b, c are real numbers always. So this is the general form of your linear equation in two variables. So why exactly is it called linear? It is called linear because whenever you try plotting these equations in your graph, you'll get a straight line, a perfectly straight line in your graph. It won't be like curved from somewhere, no. It will be perfectly straight line on your graph, and of course it's an equation. So therefore it is called linear equation, two variables. So let's see what exactly is equation and expression. What's the difference between expression and equation? I'll say that if you have 5x plus 7 is equal to root 2. So this is something, you know, it's an equation. Just by looking at it, you can tell that it is a equation. So if you try breaking this equation, you can see that x is the variable here, 5 is a coefficient over here, 7 is a constant, and again root 2 is also a constant. So this entire thing is the equation, but just simply if you have LHS, or you just simply have, you know, your coefficients, your variables, and your constants with you, it makes an expression. So whenever two expressions are put together in front of each other with an equal to sign, we have an entire equation with us. So therefore we can say always it's evaluate your expressions and solve your equations. We always evaluate our expressions and we always solve our equations. So this was the basic difference between our expressions and equations. So what exactly is now solution? We were talking about a solutions, you know, to the pair of linear equations, that is we got at x and y. So what exactly is a solution? So we say that whenever there's an x and y that satisfy both our equation becomes a solution. But for probably if you have just one equation with you of two variables, so what are the solutions for that equation? So for example, when I said that you went to the market to buy just the mangoes and strawberries, so what was the solution? So I told you linear equation is like you'll get straight line on your graph. Okay, so I had 5x plus 10y is equal to 100 with me. So if I probably, you know, try plotting it or somewhat, I'll get a straight line probably. Okay, I'm just assuming it to be a linear equation in two variables. So I'll get a straight line. So I'll always say that whatever points are lying on my this particular line, those are my solutions for that particular linear equation in two variables. So let's see an example. I'm saying let's plot this particular graph, 2x plus 3y is equal to 5. So for plotting this, what we usually do is we take our x and y's. So if I put my x equal to 0, I get y as 1.6. If I put my y is equal to 0, I get x as 2.5. If I take a few more values, I see when x is 1, my y is also 1. When my x is 4, my y is minus 1. So I have kind of points which should actually lie on my graph. Okay, so if I try plotting it, when I tried plotting it, I got somewhat like this. It's passing to 2.5. 1.6 and 2.5. So my graph is somewhat like this. So I'm getting a graph of this form. So as you can see, this graph, whatever points lie on this particular line are a solution to my linear equation, and whatever is outside this particular line, that is the entire space, the rest of the space you have, these are not a solution to your linear equation. That is, in this case we can say that 1 comma 1 is a solution to our linear equation, but 1 comma 7 is not a solution to our linear equation. Why? Because 1 comma 7 is clearly out of this line. 1 comma 7 will be somewhere above, but it's clearly out of my line. So therefore we can say that solutions are something will actually satisfy, which lies on my graph ka line only. So that's why when we saw the Tom's equation, Tom guessed that 10 and 25 is a solution. Yes, 10 and 25 lies on Tom's graph, but it wasn't actually, satisfying Dana's equation also. So that's why every point is a solution, but probably when we have another equation with us, that won't be a solution. So we'll study about that in our next class.
And so we come to an end to today's lecture. Thanks a lot for watching this, and stay tuned for the upcoming ones. Don't forget to follow @fastesthumancalculator and @exp.infi on Instagram, and subscribe to our YouTube channel.